Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the fifth video in a series on indeterminate forms and L'Hopital's rule for differential calculus. We've already covered indeterminate forms themselves, L'Hopital's rule, and evaluating limits of indeterminate forms 0 over 0 and infinity over infinity and 0 times infinity. We're now up to a point where we're evaluating limits of the form infinity minus infinity, which is one we've seen in the past. And so this is a great example of how to use L'Hopital's rule and when to not use L'Hopital's rule. So let's take a look at this example right here. The limit as x goes to infinity of the square root of x squared plus x minus x. This is definitely of the form infinity. Let me go ahead and write it here. This is infinite and this is infinite, and we're having a subtraction sign in between. So that's definitely an indeterminate form, infinity minus infinity. I would love to say that there's a quick L'Hopital's rule funness to this, but there isn't. When you have this, you just have to go back to your previous material early on in differential calculus and multiply numerator and denominator by the conjugate. So basically, do some algebra before you do your calculus. So if I multiply numerator and denominator by the conjugate, I will get the following. And we know by design, a conjugate multiplication is basically a difference of squares. So that's going to be the limit as x goes to infinity of x squared plus x minus x squared in the numerator. And in the denominator, you just leave it as the square root of x squared plus x plus x. And you get to this beautiful form here, limit as x goes to infinity of x over the square root of x squared plus x plus x. Now, let me show you when to not use L'Hopital's rule. While it looks like you could use L'Hopital's rule on this, and you could, by the way, this is of form infinity or is approaching infinity, and this is approaching infinity. So it looks like you could use L'Hopital's rule. I'm actually going to go off to the right-hand side to do this because I'm going to eventually say it's a bad idea. But let's just see what happens when you use L'Hopital's rule here. All right, so I'm going to use red ink here. This equals via L'Hopital's rule, and I'm not using red because you can't do this. I'm using red because you shouldn't do this, and you'll see why. The limit as x goes to infinity. Let's take the derivative of the numerator, 1. Oh, that's beautiful. The derivative of the denominator is 1 over 2 root x squared plus x times the derivative of that x squared plus x. So that's 2x plus 1. And then plus the derivative of that x on the back end there. The next step, I'll just do a little bit of cleanup. So this is equal to the limit as x goes to infinity. And I'm going to multiply both numerator and denominator by 2 times the square root of x squared plus x. 2 times the square root of x squared plus x. All over. When we do that, we get 2x plus 1 plus 2 times the square root of x squared plus x. Now let me just double check that I have everything correct here before I continue forward. Yep, I have everything correct. Great. Nothing combines, nothing cleans up, right? And you say, great, all right, well, look, that's infinity here. And this denominator is still approaching infinity, so let me use L'Hopital's rule yet again. There's no cleanup you could do, so let's just go ahead and use L'Hopital's rule. I'll pause the video to speed up my computation. That is the derivative, and now a little bit of cleanup here. And again, I'll pause the video for the cleanup. And we get down to here, and you can see it still is infinity over infinity. And I hope you notice at this point that what's happening is the radical is just flipping between numerator and denominator every time that we take the derivative. Essentially what's going to happen is this is going to go in circles forever and ever. So this leads to a piece of advice. Do not use L'Hopital's rule on ratios involving polynomials with radicals. And I'll write it this way. Do not use L'Hopital's rule on ratios of the form poly over radical, or radical over polynomial, or radical over radical. It just is kind of worthless to do because you're just going to go in circles. Because every time you take the derivative of a radical, it gives you a radical. It just keeps generating radicals and radicals and radicals, and you can't get out of that loop. So instead of doing that, use your old school calculus. So instead of relying upon L'Hopital's rule for this, you could just say, I'm going to divide both numerator and denominator by x. So if you divide top by x and divide bottom by x, you will get the following. This is equal to the limit as x goes to infinity of 1 over, I will write it this way, 1 over x root x squared plus x plus 1, because I divided that second term by x. And you should note, I could factor an x squared out of both of these within this radical. It would be the radical of x squared times 1 plus 1 over x. And of course, that could be broken apart into the square root of x squared times the square root of 1 plus 1 over x. And of course, the square root of x squared, normally we would return the absolute value of x, but because x is approaching positive infinity, that will be just a regular old x. We don't have to worry about the absolute values. So here's what I'm going to do. I'm just going to go ahead and say that this limit will then equal the limit as x goes to infinity of 1 over, we have this 1 over x that's hanging out, waiting for something to happen. We've traded out this radical here for x times the square root of 1 plus 1 over x. And then we still have a plus 1 off the back end. You can see the x's cancel beautifully. So I'll just write that out. Equals the limit as x goes to infinity of 1 over square root 1 plus 1 over x, and then plus 1. And now you can allow x to go to infinity. And that 1 over x will tend to 0. So you have 1 over root 1 plus 1, or in other words, 1/2. And that is what this limit becomes, a 1/2. I didn't need to use L'Hopital's rule here. It's a really good problem to showcase when to not use L'Hopital's rule, even though you have an indeterminate form of infinity minus infinity. And in fact, that will often be the case with the infinity minus infinity, is that you can't really get it into L'Hopital's form. You can sometimes though, but I'm just saying not all the time. Let's go ahead and do one more example of this type. So I have the limit as x approaches 1 of 1 over the natural log of x minus 1 over x minus 1. Now remember, as x approaches 1, the natural log of x will approach 0. And this is an odd one because if you think about it, this is approaching 0, but it depends on what side of 1 x is approaching. That'll tell us which side of 0 this is approaching. So this is one of those cases where you're going to have to break this into 2 pieces. Again, the reason why is because normally if you have 1 over something that's approaching 0, you would like to know, is it 0 from above or below? Because if it's 0 from above, then that's approaching positive infinity. If it's approaching 0 from below, well, then that's approaching negative infinity. Those are 2 completely different numbers. So I need to take this as a case-by-case basis. So let's go ahead and do that. Oops, I did not mean to make that disappear. Now I do want to say that you could actually do a little bit of algebra here before you do your calculus, which the calculus is us splitting this up into 2 pieces. If you do your algebra before, then you're not going to have the infinity minus infinity case, which is actually what I want to showcase here. So for now, I'm going to do it this way, but we'll redo this problem by doing the algebra first and seeing how that makes a difference, if it makes a difference at all. All right, this will require us to remember the natural logarithmic graph. As x is approaching 1 from the left-hand side, the y values of the natural log are approaching 0 from below. So I happen to know that that denominator right there is approaching 0 from below. So therefore, this entire fraction is approaching a negative infinity. As x is approaching 1 from below, then x minus 1 is approaching 0 from below. Again, I'll box that up and I'll just say it's approaching 0 from below. The way you can easily find that out is just take a number less than 1 and you'll see 0.99 minus 1 is a negative number. Close to 0, but negative. So therefore, this entire fraction is approaching negative infinity. And now we have negative infinity minus a negative infinity, or in other words, this is the infinity minus infinity's situation, because it's negative infinity plus infinity, or infinity minus infinity situation. So this case right here, how are you going to deal with it? Again, we have an infinity minus infinity case. The best way to deal with it is to use algebra, which is exactly why I said at the beginning, before doing calculus, maybe we should do algebra. I will actually do my algebra on the original limit because maybe something magical happens there instead of me having to split this. So that's the limit as x approaches 1 of x minus 1 minus the natural log of x all over the natural log of x times x minus 1. Now, if you allow x to approach 1, you still have 0 over 0. Oh, wait, did you hear what I just said? You have 0 over 0. So doing this algebra first, rather than saying, oh, I have to split the limit, but doing the algebra first actually saves us from having to split the limit. Because this is going to be, let's see, 1 minus 1 is 0, natural log of 1 is 0, so that's 0 in the numerator. And the denominator is also going to be 0. So now I can totally, without splitting the limit, use L'Hopital's rule. So again, this is just a great reminder. Use your algebra before your calculus. All right, this is equal to, via L'Hopital's rule, the limit as x approaches 1, we'll take the derivative of the numerator, which is 1 minus 1 over x, and we now will take the derivative of the denominator, which is a product rule, 1 over x times x minus 1, plus the natural log of x times 1. At this point, we go ahead and use our algebra, multiplying both numerator and denominator by x. So if we do that, we will get the following. Let's see, this is equal to the limit as x approaches 1. If we multiply both numerator and denominator by x, let me just go ahead and say that we're doing that here, x and x, we get the following: x minus 1 in the numerator. In the denominator, distributing through, we get x minus 1 plus x times the natural log of x. So again, we've done our algebra here. We just clean this up a little bit, right? Now, if you try to do direct substitution here, you'll see that the numerator approaches 0. The denominator, well, this chunk approaches 0, and the natural log of 1 is also 0. So this whole entire denominator is still approaching 0. All is not lost. We just have to use L'Hopital's rule again. So you could probably see there is a pattern happening here with L'Hopital's rule that you do end up using it over and over again. So L'Hopital's rule, we have this limit as x is approaching 1. The derivative of the numerator is 1. And that's actually super nice because we end up getting rid of that polynomial in the numerator. The derivative of the denominator is 1. And then we have a product rule. So the product rule, let's see, plus the derivative of x times the natural log of x. And then plus x times the derivative of the natural log of x, which is 1 over x. Use your algebra to clean things up a little bit. That's the limit as x is approaching 1 of 1 over 1 plus natural log of x, and then plus 1. As x approaches 1, we can actually use direct substitution here. Natural log of 1 is 0, and via direct substitution, you get 1/2. So this is a great example of always remembering to try your best to do algebra before you do trig, before you do pre-calculus, and before you do calculus. Initially, we were kind of stuck, but with a little bit of cognizance and a little bit of understanding that we can do some algebraic manipulation at first, we get to a nice, beautiful form of 0 over 0, and then we can start right into L'Hopital's rule. All right, that does it for this video. In the next video, we're going to deal with limits of functions to functional powers that will round out all of the techniques that you would use L'Hopital's with.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.